think they're both lame. I mean, both of them require algebra, unfortunately, right? So I wasn't trying to make an advertisement for eigenvectors, but maybe this is. Some of these problems work out easier than this one. I thought this one would work out easier, unless I'm making, I don't know. So this is, again, going to be A over S plus B over 1 plus 5S. Yeah. What's that? It's way easier to just do the differentiating? Yeah, yeah. All right, so Taylor makes a convincing point that I should bail on this and go back to my original idea, which was to use this. And since I found y, I can find what's dy dt? Ten? Yeah, 10 e to the t minus 5, 10 e to the minus t over 5 equals to x divided by 10 minus 1/10 of the y, which was 50, minus 50 e to the minus t over 5, and then solve for x. Oh yeah, that's way easier. X, now that I write it, it's like obviously easier. That's 100 e to the minus t over 5 plus, what is it, plus 1/10, well, plus 50 over 10, right? Times 1 minus e to the minus t over 5. I haven't made a mistake, which is x of t, is equal to what? Something about this feels wrong. Oh, I multiplied, you're right, I multiplied by 10, so accept that I've multiplied by 10, right? There we go. I mean, you could simplify this, but I like this answer. The reason I like this answer is it makes it obvious that when we plug in times 0, the second term is 0 because 1 minus 1 is 0. And the first term gives me 100. So we've got 100 kilograms at time 0. And what happens as time goes to infinity? E to the minus t over 5. And what are you left with? The 50. Just like over here, you're left with the 50. As we predicted from the start, eventually we have 50 kilograms in each, because you know that's kind of where it's going to go to eventually. There's a problem I like to ask a lot of times about an ice tray. So like there's an ice tray, and it's got sort of permeable membranes between the three different things. And it's fun. You can start out with different levels in each tray. And then you can write down equations very similar to the ones we've written down, where the flow from one side into the other is based on the difference in the levels of the height of the liquid in each. Maybe this is x, this is y, this is z. And then it's fun. I mean, what's going to happen from the start, right? If these are semi-permeable boundaries between the different ice tray things, it's going to level out, right? So the long-term solution has to be that x and y and z are all equal, the equal level. I like word problems like this where you can kind of see the long-term answer, the steady state solution from the start. But that doesn't mean that the math is easy, right? It's not that hard either, though. So, all right, I shut up. Because I've asked you guys a couple of energy analysis questions, so I think I owe you at least a couple minutes to talk about that, right? We talked about it earlier in the semester, but it's been a while. So let me just open up the floor for other questions. Anybody have questions about the quiz in the last, 8 or so minutes we got here? I will entertain your questions. In the absence of actual questions, I'm going to just talk about energy analysis a bit, because I think that's the thing you guys are most rusty on, is the energy analysis. Am I wrong? I don't think I'm wrong. Come on, wake up. You can do it. Is class still not canceled? Am I going to have to teach physics today? Is that what this has come to?
I mean, Liberty posted that if you're late because you're voting.
Do I not? Do I? No, of course I want to teach physics. Really looking forward to it. But I also didn't bring lunch because I figured class was going to be canceled. So now I'm in a pickle. All right. What quiz are you guys on? Quiz 4? Did I post a solution to quiz 3 yet? I should do that. I have a solution to quiz 3. I mean, I could do that. It would make the grading easier, right? Let's see here. So I haven't done anything quite exactly like problem 1 in class, but that is merely doing things that I have done in class together and logically. And those are actually kind of typical test questions, so it's important for you to like work through them for yourself. That's pretty much true of everything in here. I don't think there's anything in this that's not possibly a test question. Well, problem 9 is kind of mean as a test question, but not out of the scope of bonus questions. Convolution's a bit much. All right, so here is the question I was talking about. I want you to plot the, what did I say here? The phase plane or the Poincare plot for the given energy level. So here's a graph of potential energy, like so. And here I've given you some different energy levels. So I'll tell you one of the things. Energy 1 is below the potential everywhere. That means that, I don't really want to quite say, but I'll just say E1 is special. Okay. Oh, fine, I'll tell you. So what's the net energy equal to? Kinetic energy plus potential energy, right? And what's the kinetic energy equal to? 1/2 mv squared, right? Now the potential energy is lots of different things for lots of different problems. But if the system is conservative, the total energy is conserved, and that's what we're looking at here is, level curves of the energy in terms of position and velocity. But think about this. If the energy is less than the potential energy, is it possible to solve this equation? I've got energy is something positive plus potential energy. If the potential energy is smaller than E, which is given, can you solve the equation? The answer is no. So as we look at E1, that is an energy smaller than the potential energy, which means that's a classically forbidden motion. There is no thing to draw for E1, in fact. Sorry, I seem to be working out your quiz for you. I should stop. Now, on the other hand, these higher energy levels, there's a certain part, if you just trace a horizontal line over here, there's going to be a certain part where the total energy is above the potential energy, and that would allow to an allowed motion. For energy 2 here, if you go over here, energy 2 is below the potential energy graph, so no motion is allowed in this region for E2. All right, let me go back to the notes and look at something more that's actually worked out. So that's the one problem, is to create the Poincare plot. And then this problem is the reverse question. Here, you're given the Poincare plot, and you're asked to extrapolate backwards to go from this Poincare plot to what potential energy function you must be dealing with. All right? So this is the inverse problem, which I tried my best to draw a good Poincare plot there, but don't be a math major. Don't be too fussy. Because it's not, if you want to be picky, that's not a Poincare plot. It doesn't satisfy certain, axioms, certain mathematical truths, which must be true for a Poincare plot, because you're not that good an artist, and that's true. But the spirit of the Poincare plot is there. That is what you must find the inverse potential energy for. All right, so where were we? Oh yes, differential equations. Let's see. Let's see if we can find. Here we go. This is a good example of a Poincare plot and the potential energy. So up on top, I have a given potential energy function. Looks kind of like a tooth. And here's some different energy levels. Energy -2, energy -1, energy 1, energy 2, energy 3 perhaps, with color coding. So energy 2, the net energy of -2 is only larger than potential energy to the right here or to the left over here. That corresponds to these possible motions down here. All right? Then energy 1, for example, this blue, there's motion allowed over here, which corresponds to this. And then here, you can bounce back and forth in this potential well, which corresponds to this little elliptical trajectory down here in the phase plane, in the XV Poincare plot, like that. And then over here, that's coming from this. Where the energy level meets the potential energy, that means what? If energy is equal to potential energy, that means the kinetic energy is 0. Kinetic energy being 0 means the velocity is 0. That's why these intersection points should properly match up with the velocity being 0 down here. See, this is the velocity. So velocity 0 means that the kinetic energy is 0. Kinetic energy 0 as any of these things cross the x-axis, right? So like going back up to here, all right. How do you guys put up with this? I don't. I'd say go vote, but if you're not complaining about this, should you be voting? I don't know. I don't know. Let's see here. I mean, where was I? So this is a stable equilibrium, right? Because if you're close to it and you get nudged a little bit, you just bounce back and forth between this potential well. In contrast, these are also critical points. So critical points are special. You can see them in either plot. Like a critical point in the for the potential energy is just like a critical point in the sense of calculus 1, right? A max, a min. Those also correspond to critical points in what's a critical point for a system of differential equations? A critical point is one at which both of the derivatives are 0. All right? And if both of the derivatives are 0 in this kind of system, it turns out that that has to happen on the x-axis because one of our differential equations is just that dx dt is equal to what? What's dx dt equal to? This is easy. You could answer this without differential equations. Velocity, right. dx dt is equal to v. So if you want dx dt to be equal to v, to be 0, that means that the critical points in the xv system have to lie on the v equals 0 curve, which is the x-axis. So critical points in the Poincare plane have to lie along here. In this case, there are actually 3 of them. This one, that one, and that one. These 2 are unstable, and this one's stable. The unstable ones, you can also see that they're unstable, see, because one of these solutions flows in, but the other solution flows out. So depending on how you get nudged off this equilibrium, you're either going to go one way or the other, right? You get nudged a little bit off that equilibrium, you're just going to stay there, right? So the deeper study of stability is an interesting and rich topic, which we don't really get into too much here, just enough to get into trouble. So I'll shut up. Anyway, next time, partial differential equations. Or do we have a test? There's no more tests?
Okay.
I feel like there's a test in here. You guys are tricking me. You say it's real life next week? What did you say?
Because it's the day after abstract.
Oh, the day after abstract. Like that's like the day after the world ended or something? Or let's see here. Let's see here. Allegedly, I'm giving you guys test 2 on, what's today? The 6th. So we've got Thursday and awesome. Yes, the last class before Thanksgiving break, we have test 2. We're actually a day ahead. Woo! So we'll get far into PDEs so that you actually probably have a chance to work on the PD project over Thanksgiving break if you feel like it. Because I know you're going to have a bunch of engineering projects after Thanksgiving break raining down upon you, am I right? We're almost into the season of engineering projects right now. Putting the test 2 this far is already dangerous because we are entering the season of career fairs and engineering projects, which take precedent over math, right? Don't agree to that. Hey, oh, you're actuarial people. I forgot. You can cut it off, Ian. I'll stop making noises.
I was going to ask you,
You hit,